Swayam Prabha. Digital India. Educated India.
Right? What is the other one? That's 10, right? And then what about 11? Which one? Yeah, go ahead. So you want to write something? Oh, we didn't do 9. That's what I'm wondering. Yeah, because one number is less. So let's do 9. Sorry. 9 is how much? 3, 6, 4, 5, 5, 4, 6, 3. That's it. And then you have 10, which is 4, 6, 6, 4, 11, 6, 5, 5, 6, 12, 6, 6. You see, the distribution is beautifully symmetric about some value, right? It's symmetric about some values. Now, I have 100 dice, okay? I throw them as many times as possible. Obviously, 100 dice will have very remote possibility that all the dice will show up phase 1. Okay? Only Sahuni can do that. Okay? In Mahabharata. Nobody else. He is the only one who can call exactly what should be the throw that would result. And therefore, he always wins, right? Remember that, right? Now, if you look at this, you see the middle value. Which is the middle value? 7. As the maximum probability. What is the total number of events? 36. What is the middle probability? 6 by 1 by 6. All the others are lesser probability. Okay. So what happens is that when you make measurements on systems, certain things are more probable than certain other things. Okay. The probability comes into the picture. Whereas in a laboratory, if you repeat the same experiment, you must get exactly the same titration value, which is called concordant titer value, isn't it? Concordant, you are familiar with that. That's because the real physical systems, we don't understand the microscopic averages, but finally what we see is what is predicted. There are errors between concordant. That is the reason why they say you must make the same error both times in order to get the same value. Okay, you never get the true value. You get an average. Okay? The true value is not part of the measurement process. It's something else. Unless you know already what is the true value. Okay. What is important is that the probabilities are there for different outcomes in any given experiment. That's the whole point. Okay. Now, some experiments, the probabilities may be the same all the time. And the most famous example, our movie example is, I don't know, I belong to the older generation of Sholay. I don't know whether you have seen the old Sholay these days, but if you saw the new one, there's no connection to that. And here is Amitabh Bachchan holding that coin and always calling head, and he always wins. Dharmendra, doesn't know why Amitabh Bachchan wins all the time. What's the secret? What's the secret? Both sides the coin was head. When does he find out? After Amitabh has died. That's why he says, this guy knew his game very well. He had tweaked the system so that no matter how many times you call, you will always get the same result. Such a system in quantum mechanics, when you make repeated measurements and you get the same answer, then that system is supposed to be in the eigenstate of the quantity that is being measured. And the value that you get is the eigenvalue. Okay? So the eigenstate is a state which no matter how many times you repeat measurements of that property, the eigenstate is an eigenstate of a property. Please understand. It's either the property is total energy, or the property is total momentum, or the property is total angular momentum, something else. But for each one of them, there is an operator. And that operator acting on that eigenstate gives you the eigenfunction, same eigenstate, times an eigenvalue. If the system is in that state, for that operator, no matter how many times you throw that coin or measure the system, you will always get the same answer. So the eigenstates are invariant system properties. Invariants. They are fixed. You will get only one or the other. If you do this experiment thousands of times, okay, that is the two dice, if you throw, yes, yeah.
If we have more than one eigenvalue, we will get
either one or the other, subject to the probability here. For example, see here how many outcomes are possible? 11 outcomes are possible. Okay, first outcome is 2, the last outcome is 12. So there are 11 outcomes possible. Do they occur with the same probability? No, that's the point. Therefore, quantum mechanics tells you that if we do not know the state of the system, then whenever we make a measurement, we get an eigenvalue of that measurement. But will it be the same eigenvalue all the time? It will not be. It will be only if that system was already prepared as an eigenstate of that measurement. Already. So, this is a fundamental property, and the fact that every time you make a measurement and you get a different result subject to the laws of probability was beautifully stated by Max Born. Okay? So, he said the wave function is not what is important for us. The wave function must be calculated, must be found out, but it is the absolute square of the wave function which is relating to the probability of the outcome. The absolute square of the wave function. Now, the wave function, for example, if you think about a system in this room, you have dimensions, okay? 0 to some distance, 0 to some distance, and 0 to some distance. So you have physical dimensions, which we can call as the 3 coordinates x, y, z. Therefore, the wave function for any system here may be a function of those 3 coordinates x, y, and z. Now, what does this psi square tell you is that psi square is the probability density. Density. It is not the probability value, okay? It's a density. Let me not erase this. I need this for another discussion. So, we'll keep that at the top. Now, suppose you have a particle in between the two limits. The particle can only be found between the two limits. It cannot be found elsewhere. Suppose we have a very special case, and we calculate for this particle the h psi is equal to E psi. Okay, what you see is that the absolute value of psi square, if this is the coordinate x, this interval is dx. Okay, smallest, narrower and narrower, the smallest possible interval is dx. Therefore, the psi square measured at x plus dx, psi square dx, is the probability that when you locate the particle that it will be in this interval. Psi square dx is the probability. Now, this will be one number, this will be another number, this will be another number. They may not be the same. Probabilities need not be the same at different intervals. They may be. But if I calculate all the probabilities together, I add them all, what should I get? Because the particle is somewhere there. Okay? Anywhere between these two limits, the particle is there. Therefore, if I calculate everything, then between 0 and L, it should be 1. This is the analog of what you call as the normalization of the eigenvector. This is the corresponding analog statement. So, this is called the normalization of the eigenfunction. Psi?
Psi bar.
Psi bar is what? Psi star.
The dash on top.
I didn't get it. Oh, no. Oh, yesterday I was talking about. No. That psi bar is only a notation to tell you that wave function is different from this wave function. Any one of them. See, you can use, suppose you define your psi by this equation. Okay? Then you must define for the same system, it's not that, it will be this to indicate these two are not one and the same. That's all you have to remember. Okay? Which one you do where is irrelevant. The wave function which is time dependent wave function for this equation, for the same Hamiltonian, the time independent wave function will be different from this. That is all you have to remember. Okay? That's what I think you were asking. Yeah, this is fine. Yeah. So now let's go back to the question. Where is my duster? What did I do with my duster? It's interesting. Disappeared. Yeah, go ahead. Wait.
Okay.
Right.
Does this integral imply that the particle is always within these bounds of O and N?
Yeah, assuming that it cannot escape those boundaries.
Okay.
Suppose the boundaries are larger. You
Like
put
the
the whole
universe.
boundary. Okay. Suppose the particle is anywhere in the world. You put from 0 to infinity. No problem. Or minus infinity to infinity if you want. Doesn't matter. What is important is you define a boundary. The particle cannot escape the boundary. It's a boundary which brings in what we call as the quantum numbers to the system. Without the boundary, there are no quantum numbers. So the mechanics of atoms is that for each of these systems, we define clearly what are physically accessible boundaries. And if the boundaries are not very, very strong, the particles can leak out of the boundary by some other means. We call them as the particles have tunneled their way through. So it's possible, but that's because the boundary is not infinitely short. I mean, if particle has very high energy, it can cross over any mountain. But if you say my mountain is infinite, touches the sky, and you cannot cross, obviously you are confining the system to a very small region. Such models are starting models for understanding quantum mechanics. But the real model, for example, in hydrogen atom, for the electron can be anywhere in the universe, still attached to this hydrogen atom in a small way. Therefore, when you talk about the electron probability density for the wave function, you will say the three-dimensional world is the limit. Universe is the limit. So you say x is minus infinity to plus infinity, y is minus infinity to plus infinity, and z is minus. There's nothing beyond the infinity. Okay?
Yes.
So that's the meaning of what is called the constraints or boundary conditions of the system. Okay? Yeah, go ahead.
Sir, in the integral, are you referring to the probability density or the probability, sir?
Probability density. The psi square is a density. Psi square is a number. Psi square can be 0. But psi square at one point will be 0 if the function has a node at that point. But the function will not have a node along the whole line, except when you come into multidimensional surfaces. You can have a node across a whole line. But then the area is what is important for multidimensional surfaces. The volume is more important. Instead of dx, what is called the smallest element of surface will be the area, dx dy. Smallest element of volume, if you take it, dx dy dz. Therefore, the wave function may be 0 at a given point. The square of the wave function therefore will be 0, but the wave function is extended. It's not 0 everywhere, it's 0 at some point, but it's obviously something which is non-zero. So the psi square dx dy dz or dx will never be 0.
Okay, sir.
At any point it will never be 0. Therefore, no matter how small your volume, just one moment, no matter how small your volume element you choose, there is a finite probability that you will find the system in that. But if you choose a point, the probability for such a continuous distribution doesn't make sense. Therefore, the function may be 0, but the density extended over a volume or an area or a length will never be 0. Yeah, you have a question.
So within the given limits, we know that a particle exists. So the probability density after adding all the like probabilities at each and every point, it will be 1 in order exactly. So why are we using an integral instead of a summation regular summation?
But x is any possible value. How would you sum a continuous function?
We could take from the origin to like
Continuous function, whatever it is. See, your starting point is some number. You call it a 0 or you call it as minus infinity, you call it this, it doesn't matter. What is important is there are two boundaries. Define the boundary, but in between the variable is a continuous variable. How would you sum a function which is continuously changing? That's the integral, that's the definition of the integral. When you remember, you take a finite curve, you put small squares, but the squares will have either go over the curve or will be below the curve, so there will be some area problem. And so what do? You make the square smaller and smaller and smaller. What is the limit?
extends to 0.
The area goes to 0. And therefore, the integral, the sum that you write, that's what that is. Okay. The sum becomes integral. There is no sharp thing. Okay. Sum goes over to an integral. Sum is defined when you have discrete terms. I have a point here, this is the value. The next point is here, this is the value. In that case, you sum it up. But in between, if you have that, obviously the sum has to become continuous. And so, the integral is the corresponding exact mathematical limit for taking the sum of a continuous function. Okay? Yeah. So, yeah.
Sir, here we have integrated from lower limit 0 to upper limit L and we're getting 1, sir. So, but then since both of them are just boundaries, we just integrate with lower limit L and upper limit 0, we'll get -1 here, but...
I mean, probability, do you want to say negative probability? What is probability?
Sir, I mean like, but those are boundaries, but then if we integrate like that, we get -1, like how is that possible?
No, the integral, there is nothing, see, so that's actually a good question, okay? So, there is nothing called a lower limit or upper limit. You are integrating the square of the function between two limits. But if you want to make sense to the probability, the number that you should get should be a positive number. You choose the limits accordingly, okay? That's it, that's the answer, okay? It's a very simple thing for 0 to L. If you do that, that's because we assume that the function is 0 at 0. The function is L also 0. Function has to terminate. Function cannot have a finite value at the boundaries. If it has a finite value at the boundaries, then it may go outside the boundary after that. Therefore, the function terminates at the boundary, goes to 0. So these are essentially the mathematical elements that enter into the description of the atomic mechanics. Okay. So, yeah, if you say that L to 0 psi square dx is -1, I mean, I wouldn't worry so much about that. Okay. All I would say, you want a function to be normalized, do it for the positive. The negative numbers are important in some other context. But here, hey, I still am losing my, maybe, no, it's not here. Where did I put my, oh, it's over. No, not there. I must have walked across the table somewhere. I didn't? Is it underneath? No. I moved it up, I know. Ah, there it is. I know. It's tiny. Okay.
Sir.
So, yeah, go ahead.
Sir, so the absolute square of the wave function is the probability density. That multiplied into dx will just be the probability.
of finding the system in that dx, x and x plus dx.
So once it's
It's for one
multiplied by-
dimension. The
once
same
it's-
thing can be done for a volume area.
Once it's multiplied by dx or dx dy, it will give the actual probability.
That's the actual probability. The probability density is a number at each and every point. That number can be 0. But the area, see, if you take any graph, suppose the graph has a point at which it is 0. Please remember, it's at one point that the graph will be 0. Okay, let's assume that this is psi square. As an example. See, at this point it is 0, but it's at a point. Any point nearby, there is a finite psi. So, psi square dx is that area. Okay. In this case, of course, it's just a dx. And in every other case, it's the mid-value psi multiplied by the square multiplied by the dx. Therefore, the area under this curve for any finite interval will never be 0. Therefore, the probability of finding the system in any small interval cannot be 0, but the probability density at a given point may be 0 because the function has nodes. I mean, nodes are allowed, functions are allowed with nodes in the solution of the equations. What is not allowed is infinite number of nodes. Okay? There are things that you have to worry about. Yeah. So the idea is that now connect whatever I said to this. I'm almost finished, okay? Another 2 minutes or 3 minutes. Connect whatever I said. That's discrete. When you said sum, there it's a sum. 1 by 6, then you have what? 1 by, what is this? First one is 1 by 6. The second one is 1 by 4. No, there are 11 evens. 36 evens. And so you have 2 by 36 plus, what is the next one? 1 by 36, isn't it? First one is 1 by 36 plus 2 by 36 plus 3 by 36 plus 1, 2, 3, 4, 5, 6. The next one is now 5 by 36 plus 4 by 36 plus 3 by 36 plus 2 by 36 plus 1 by 36. It's 1. Okay. So you see the distribution that the probabilities are not uniform. Even for a discrete experiment like what you have done, the probabilities are not uniformly the same for each and every event. The event is, my total should be this, that's the event. That's your outcome. My total should be 1, 2, my total should be 3, my total should be 12. Then the moment you have defined your events, you see that the outcomes do not necessarily have the same probability. Same way, in the measurement process in quantum mechanics, you decide my outcome is to be one of the, obviously when I measure, I get one result. I don't know the outcome. Here, of course, I know the outcome. In quantum mechanics, very often I don't know the outcome. But the moment I measure it, I see that the outcome gives me one eigenvalue. Now, what is most difficult for many people to understand at that point, and Einstein was very unhappy with the whole idea, is that the system after the measurement is not the same as what you started with. Now it has become the eigenstate of that measurement. From that point onwards, if you measure that system, it will always give you that value. Okay. So you have changed the measured system from the outcome. In classical physics, we don't need to worry about that. We can measure things without disturbing them. You know, from a distance, you can observe from a distance the microscope, you don't change the positions and momenta of the planets and so on. You think you don't. But eventually, all world satisfies quantum mechanics, okay? Whether it is planets or whether it is stars or whether it is galaxies, they all satisfy quantum mechanics. The changes are not observable. Therefore, we see that the measured object is not disturbed by the measurement process. That's very important. That's our classical world. We can snoop into somebody's room without the person realizing somebody must be watching me somewhere. Okay? No. In quantum, the moment you make a measurement, you have destroyed sometimes the original nature of the system and you have fixed it to the state in which you got the outcome. It becomes the eigenstate. Therefore, the measuring process determines the measured outcome is something that people didn't like. It's a very philosophical statement, but you don't, I mean, it's how relevant it is for other things, I don't know, but every time you do quantum mechanics, you will see that the eigenvalues and eigenvectors and the measurement processes are the fundamental concepts of whether it is electron density or whether it is the electron polarizability, dipole moment, whatever that you can measure chemically using quantum mechanics, they all will have the implications back on what are called their wave functions corresponding to that problem and what are the outcomes and so on. So please remember that this is the first exposure to some such thing called the probability density, and quantum probabilities are usually continuous, but in the case of spins, they are discrete. The spins will have not continuous outcomes, they will have very special outcomes. Someday I will talk about magnetic resonance and the electron spin and the nuclear spins, and then I will tell you that that experiment is more important for the measurement of spins and what we call as the qubit or the quantum bit, which is today making a lot of waves for the quantum mechanics and the quantum computers and the discovery of quantum computers and so on. All these things are fundamentally related to the description that I gave you for a short while. Okay, so that's the relevance of eigenvalues and eigenvectors. So let me stop here. If there are any questions, otherwise, I think the next speaker is already in. Who is the next speaker? Is already there? Hey, need an extra? Yeah, well, come, you can come in. Come. I'm done. Break up. Normally come break. So if you have any questions, so Kodan Raman is already here with you. Yeah. Yeah.
What did you discuss?
Oh, I discussed the probabilities. Discrete and continuous. Fine. Cholet's experiment. There is no probability. Probability is always 1 or 0. Yes, yeah. Mike. Yeah.
So you said that when you measure a system, you are changing it into an eigenstate and you are not going to be able to get any other eigenvalues than the one you ended up with, right?
No, but if you repeat that experiment with an identical system, you may not necessarily get the same eigenstate.
Okay. So,
You understand?
so in that case, for us to obtain all the eigenvalues, does it necessitate that we need identical systems?
The eigenvalue determines the state of the system, the outcome, the eigenvalue measurement that you get. The system will be in the eigenstate corresponding to that eigenvalue.
Yes, sir.
But the problem is that eigenvalue has a certain probability of happening, like the probabilities that you saw in the discrete measurements. One is 1 by 36, the other is 2 by 36 and so on. So suppose you did the experiment 100 times. It is possible that X number of times you get one eigenvalue, Y number of times you get another eigenvalue, but each of these systems will be fixed into those corresponding eigenstates. Therefore, your process of measuring the system is going to uncontrollably affect the system's behavior after the measurement. That is what was called the measurement problem in quantum mechanics. Okay? Yeah. 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 Any other? Yeah, she has one more question. Yeah. Go ahead. No, you can. Yeah, Sir. Yes. Yeah, hand over.
Sir, depending upon the systems, you said like that's one particular eigenvalue for that particular system, right? So as we now discussed, if it's going to change every time we are going to measure it and get different eigenvalues for the state in which the system is actually there, how do we decide what one value will actually be there for the system?
There are two parts to that question. Question one is you have one system and you have one measurement. Question two is you have 100 copies of the same system, but you are measuring each one independently of the other. If that's the case, the second case, you have 100 copies, not all the 100 copies will give you the same result. Some of them will end up in one eigenvalue, some of them will end up in another eigenvalue, and therefore you get a distribution of the eigenvalues. The distribution and the number of times each eigenvalue happens is dependent on the probability that that eigenstate will be obtained when you make a measurement. So, for a single measurement, one time you have measured, you have destroyed its character. You have fixed it into an eigenstate. Now, the third related question is, if all the 100 systems were in the same eigenstate to begin with, let me now make a measurement. All 100 of them will give you the same result. Nothing will change. Because the operator that you are using to measure, this system is an eigenstate of that operator. Therefore, there are many different ways by which you can approach the measurement process. The outcome determines whether the system was in an eigenstate, and if not, if it was in a linear combination of many possible eigenstates of which one of them is an outcome. That linear combination is something, if you want to understand, one moment, if you want to understand, read the first chapter of third volume of the Physics Feynman lectures and lectures on physics. Third volume, the very first chapter, it talks about the quantum property of the experiment, of the double slit experiment, and it tells you how the electron is possibly in a combination of two possible outcomes. When you add the two wave functions, it's a different thing. When you add the two probabilities, 2 psi square, it's a different thing. It's like psi 1 plus psi 2. If you take the square of it, it's not the same as psi 1 square plus psi 2 square. And that's what happens when the system is in an arbitrary state. We assume that it may be in various possible eigenstates with a certain probability. And that probability measures when you actually make the measurement, that shows up in the measurement. So, question is very, very difficult to understand that every time you make a measurement, you are no longer allowing the system to behave independently of what you do. Your act of measuring changes its character, which is not what classical physics is supposed to be, which is not what classical chemistry is supposed to be. But the quantum mechanics tells you the measurement can destroy the measured quantity. Okay? Yeah.
Thank you, sir.
Yeah. Thanks. Yeah, 2 questions. Quick. Yeah, he also. Yeah, go ahead. No, go ahead. I'm okay. Yeah.
So we need multiple systems, right, to get different eigenvalues. Like sometimes we might end up with the same eigenvalue, but for 2 systems to be identical, what are the properties they should share? Like the same particle,
Okay.
but then...
Yeah, there are what are called consistent quantities. They are called quantities which can be simultaneously specified as properties of the system. And one thing that cannot be specified as properties of the system is a value for the position of the particle and the value for the momentum of the particle at the same time. These two cannot be given as attributes to the particle. So, what are the attributes that we can give to this particle? You will find out the answer lies in the operators corresponding to the attributes. If those operators commute among themselves, then all the eigenvalues of those operators can be attributes to that property. And momentum and position do not commute, therefore these two are simultaneously not attributes of the particle. Angular momentum, x component, and maybe position of the particle, they commute. We don't have a problem. You take the 2 particle system, the center of mass of the particle, which is the coordinate, and the position of one of the particles, if you take, they commute. So, idea is that the properties that we can describe before making measurement are limited by all those operators associated with the system which commute among themselves. This is known as completely commuting set of operators in quantum mechanics. The first person to introduce this terminology was Paul Dirac at the age of 28. He did that, okay? Yeah, thank you. Yeah. Okay, so I'll continue. I don't know whether I can explain, but you have a great experimental head and someone who does real things.
Everybody doing really things.
I live in my own world. It's real for others. I mean, for me, it is only calculation.
Your eigenvalues are real.
Eigenvalues are real, yeah, that's right. Okay, so take care.
Sure, sir.
I'll see you then. So, tomorrow my lecture is not scheduled, so Prasad will do it. I've done 3 hours. I think you can also see me off a little bit. I mean, you get tired of me as well. Well, now it is.